Good morning. This is the last regular day of class. We will be doing a lot of different things today in preparation for the final topic, which is the fast Fourier transform, or DFT actually, the final project, of which there's two to choose from. The final homeworks, which are in process for last week's lecture on filter and network topologies, and then to be followed by a few problems on the DFT and FFT, and then the project, which will be due after the final of next week, and then the final of next week. So as a quick refresher, I just pulled this up from the website. This is the final exam schedule. We're a Wednesday-only class. We normally meet 8 to 10:40, so we fall into this window of 8 to 10. Nothing exciting. It means for those of you that have rarely gotten here by 8 o'clock, you're going to be on your best, should be on your best behavior to try to get here and utilize the time. I will be here the full amount of time, but I can't stay later than that because you can see that in theory there's another session coming in at 10:20. So now that that's over with, and I've got a review sheet that I'll be going over later. I said I'd have a paper copy last night on the website, and sure enough, here it is. It'll be useful because I'll probably take some notes on the electronic copy, which I'll repost, but that way you can write notes or highlight things. I highlighted a lot of stuff in red already, but there might be other things that I'll say or in response to questions, and I'll end up drawing on that document when we get to it. Okay, where to begin? Based on not a lot of people here right now, I was going to go through the histograms immediately, but I think I'll delay on that. I've got those prepared. I pushed back the exam 2 as well. And the next topics could be talking about the project and what you will decide to do. First, let me say the grading of Project 1 is something that I would never have been done with at this time. If I had like 15 people in class, which is about what I had 2 years ago, it's just a massive amount of grading. As you know, there's a massive amount of work put into that. But those always get done. In theory, I should get done with things faster. I did myself dump a lot of time into creating the second project. So I wrote some comments yesterday, and of course I type in a hurry and don't proofread correctly, so I look at this and I see I hacked up my writing again. But I think the points are there, that there are two projects. There's a project old, as I've called it, and on the website it comes up with the label Project 3. It's just because of the way the file was named way deep inside on my computer. But Project 2, Project 3, whatever. There was a new and an old, and then on the website further down I refer to it as A and B, which is probably more confusing, but it's just what I was doing when I was writing away. So we have option A and option B. And we talked through a lot of the new Channelizer project last week. It does have about a 500 megabyte software-defined radio sample file download. It's on Slack. No one has pulled it down to let me know that it comes off of Slack okay. It went up okay, and I can see it on Slack, so I'm assuming, let me get rid of this. This is it right here, though. So if you decide to go with this project, this is actually, in my opinion, the easier of the two projects because it's not any serious coding of algorithms. The adaptive filter project is a tried and true project. It does take a little bit more effort to develop the algorithm and code it, but I supply lots of details on it, whereas this one is more or less out of the box, just following the steps that I put in. I'm going to save going into the details on that until later because we don't have very many people here right now. But both of them have the same setups. The only difference is with option B, or the new version, I also have a rendering of the PDF notebook, or of the Jupyter notebook, and this has a lot more content on what you're going to actually do. That sample notebook is pretty much all good to go. You just have to start using it, and a lot of the experiments are just around that notebook. So I didn't put all of that into the reader itself. I just didn't want to dump the time into that because I wanted to keep moving with my schedule. So we'll come back to that. What I will do today, though, again, when more people are here, I'll look at Project 2A on adaptive filters. Last week we did 2B, and I ran demos and played audio and things such as that. I'm not going to do that again today, but I did not do any of that for the option A with the adaptive filters. So I've got that all set to roll out. I've got audio files that will play and plots and things. So those of you going down that path will see what I expect to have there. Okay. I'm going to go over the histograms. I'm going to talk about the final review and all that stuff later in the class. I think probably the best thing to do right now is to just jump into the final topics, which is on the FFT. So we start with the DFT and then move over to the FFT. So I've got that set up in here already. Some topic has to be at the very end of the semester. If you were to say, and I'm just saying philosophically, you would say, we can't be doing anything new on the last day of class, then we'd be throwing out a whole day of class, and I don't believe in doing that. But some topic, needless to say, has to come at the end. And this is a very good topic. It's one of the pillars of digital signal processing, the discrete Fourier transform and its efficient implementation using the FFT. I've tried moving it in the middle of the semester and then would have finished on the topologies we did last week. That worked okay, but I decided on this fall 2024 I would just stay with the flow that the book has set up. So we have a lot of properties associated with the DFT, so we talked through those. That's the 7.4 topic here. First off, we have to get into the definition of it, and then we'll see what are some of the implementation things you can do. Filtering is one of the things that you can do with the FFT. You can do what's called transform domain filtering, and in fact, the channelizer or filter bank idea that's in Project 2B, or the new Project 2, it does exactly that. So I kind of did that on purpose, but not exactly on purpose. It just seemed very convenient to try to explore that. And then there's other applications besides transform domain filtering. Probably one of the biggest topics is, trying to think, do I have it in here? The other big topic besides transform domain filtering is spectral analysis. It's a huge topic, actually. It's used all over the place by people that do signal processing development and implementation. It's the way that we can get our eyes on the frequency domain conveniently using DSP. So, and that'll be brought up when I go through the review sheet, because there's some really basic ideas about spectral analysis with the FFT that I cover, and I have it synopsized at the bottom of the review sheet. It's a very simple, back of the envelope type calculations, and I just can't not walk away with a semester without having you see how to do that and being able to practice it on the exam, because it's such an easy thing to do. It's not complicated at all. It's, like I said, back of the envelope calculation. So what is the DFT and the FFT fast, efficient implementation all about from a signal processing point of view? First off, I want to refer to it as a DFT. It's typically implemented efficiently using an FFT, but it has an underlying concept, and that's a review sheet. That'll be later. I've decided to do that later based on the attendance so far. But what do we do with the DFT that makes it special? And up until this point, we've had the Fourier transform of a sequence, but if you remember, that's a continuous function of frequency, and to get back from the Fourier transform of a sequence, we have to go through an integral. The DFT is a huge improvement, because what you can do with the DFT is effectively sampling in the frequency domain, and then you can go back to the time domain with a numerical algorithm as opposed to having to integrate. There are some nuances that go along with that. So the starting point that I like and the book likes is just consider this finite length sequence. So that's kind of a necessity when you use the DFT. You can't have an infinite length sequence except if you do a piecewise operation, and transform domain filtering does take advantage of that. But just thinking of a finite duration sequence, n samples long, if we Fourier transform that sequence, which we could have done back in Chapter 2, we would just evaluate it in this fashion. We would just take the n points where it's non-zero, sometimes called the interval of support, and multiply by e to the minus j omega n, and then we would have our traditional x of e to the j omega. Continuous function of frequency, we can evaluate that at as fine a resolution as we want. But is that practical? Well, it depends on what you're trying to do with it. But what we consider for the DFT is sampling just at a set of n frequencies, which correspond to omega k being 2 pi k over n. So we just take n frequencies, and they're actually, if we think about this e to the j omega naught, we're sampling around the unit circle at those n frequencies. So when we get it evaluated at the discrete frequencies omega sub k, we end up making a substitution in here, and that substitution is w sub n is e to the minus j 2 pi over n. So these are sometimes called the twiddle factors that are used in the FFT, because they're just discretely stored values of e to the j omega. And that ends up being part of the way you calculate an FFT, having usually a lookup table or stored values of those complex sinusoids. So this picture right here, Grant, go ahead and take one of those. Actually, take both of them, because the other guy usually sits closer to you over there, right? And you'll be able to hand it to him. So this picture really explains what's going on, though, with the DFT. So we have some function of frequency. I just drew it as a periodic continuous function here, 0 to 2 pi. We take and sample it at n points. We go 0 up to n minus 1. This is just a repeat, so we have the unique point, 0 to n minus 1. If it's a real function, this is even in magnitude, but if it's complex, we need all n points. So don't think, in general, you can get away with just n over 2 points, but at any rate, n points. And now we have, in the z domain, we're effectively sampling around on the unit circle at those points, 2 pi over n spaced. And that is all there is to the DFT. So if we have an n-point sequence, we have n points in the frequency domain. And right now, we're not looking back immediately, but we will in a second here, to what goes on when we don't have all of the points. So we're effectively sampling in the frequency domain, and surprise, surprise, we have the potential for aliasing back in the time domain. It's a symmetrical kind of relationship, but we're going to learn how to deal with that. So what we have the so-called analysis equation, which is what we just went through. If we're working with an n-point discrete Fourier transform, we just go through this operation here to get the n frequency points, which are complex, capital X of k. The inverse DFT is a very similar operation. I haven't proven that yet, but that's coming up in the next page. It's just going to be taking a similar sum, and we have the minus sign in the exponent of the total factor weight. And the only thing that's different otherwise is we have a scale factor of 1 over n that we have to go through when we go back from the DFT points to the sequence domain. So to prove that this works, I just put inside the inverse DFT equation, I'm putting in the forward DFT, which is inside the square brackets. Then I do a rearrangement, change the orders of the sum, do the sum on k on the inside, but then I notice that this sum on the inside has the very special property that it has a chronic or delta-like behavior. In other words, when m equals n, this thing becomes 1 because we just have 1 inside of here, and we sum that up and we get n over n, which is 1. But if n does not equal 0, we're summing n values around the unit circle of a complex sinusoid, and that will average out to 0. So we get, in fact, this is the result right there. We get back to the sequence x of n. Right away, without me saying anything more, and maybe just backing up to this, the hugely important deal with the DFT is explained in the fact that we can go into the transform domain with a numerical calculation. We can come back from the transform domain to get back to the sequence domain with a numerical calculation. This should be like, if this is the last regular lecture, but if this was the end of your being a student in a class, this would be like, wow, I've been waiting all these years to finally realize that the Fourier transform is not as bad as I originally thought. I don't know, think back to in circuits when you first learned about the Fourier transform. It seemed exciting. You could do convolutions by multiplications, but still you were bothered by pesky integrals and having to do things of that nature. This tells you I don't have to do any integration. I can do it all numerically, and like I said, there's nuances, but this is huge, and so that's why I refer to this as one of the pillars of DSP. The fact that this exists has been utilized by everybody everywhere. I mean, many, many years ago, when I was involved with doing stuff for Hewlett-Packard, and then Agilent, never consulted directly for Keysight, they had me into a class in the Scopes division here in Colorado Springs. I don't know, does anybody know that up in Briargate off of Union Boulevard way up north, before you get to Research Parkway, there's a big building on the right? They just built some apartments in front of that. I go to that YMCA up there since the one by my house over here in Garden Ranch closed, but that was a division of Keysight, Emergent, or not Emergent, but Agilent, and then Hewlett-Packard. So the Scopes division was there for a while, and that's where I taught one of my short course classes. It's a building that looks, now that I've told you that, look at that building and then go out in Garden of the Gods and look at the buildings out there. You see a certain style resemblance, I think. It's a company that made classy buildings for their engineers. What's that?
That shows revenue.
The fact that it's big and nice looking, yeah. It hasn't been occupied for very long. I think a check printing company was in there for a while. I don't even know if it's occupied at all right now. If you don't live up there, you don't know what I'm talking about, but some of you are nodding your heads like you know. You know what I'm talking about because you're newer. Okay. It brings back memories every time I drive past there going up to the Y, which is just up Research Parkway and then wind around over there by King Soopers. So I'm driving up that way a lot. At any rate, this is huge. So now that we know that this exists, we have the DFT pairs. What can we do with this? First off, one of the things that we have to be aware of is that when we go to get the sequence back from its Fourier discrete Fourier transform effectively coefficients. And by the way, these coefficients x of k's are actually like the Fourier series coefficients in an expansion, which takes you back early in time, but early in your time of being an EE. I say that's another philosophical thing. Most of you have either graduated with your bachelor's or are soon to graduate. It's time, if you haven't reflected, you can reflect anytime you want to on how you've been transformed by going to school. It's either a good thing or it could be a bad thing for some people. It's like, I'm never going to do anything with my degree, but I learned all this cool stuff. But on the other hand, you still were transformed. And if you went to school to become a lawyer, you'd probably be transformed too. I never had any aspirations to be involved with law, but I do have a nephew that, pardon me?
Patent engineers.
Yeah, exactly. And I've worked for patent attorneys before and that sort of stuff. I'd rather be at the grassroots level of problem solving. But some of you will give that up and become managers and manage people, and you'll probably say, yeah, I want to do this because I'll get paid more and I won't sweat as many technical details, but you'll have to sweat all the personnel and all those other things that all of my former students tell me when they grow up to be managers. They say, I spend so much of my time dealing with people issues, which is really our life anyway, right? We don't just work in a technical domain of being abstracted from reality. We have to work with people. But it sure is fun to be able to just kind of do your own thing, but you don't get to do that all the time. So one of the things, though, that happens, and if you look at the way the math works, is that the DFT has a modulo n property. Whenever you're wanting to look at points on the DFT axes in the frequency domain side or the time domain side, there's repetitions. And the book puts this tilde over the waveform or the transform to signify the fact that there's what they call periodic extensions. And I think I have a picture of that. I guess I don't have it right here. But if you were to draw this out, once you go to the transform domain, if I get this working again. I guess my pen is not wanting to work at this moment. Not as expected, at least. Thought I had a neat picture of that in here somewhere. Actually, I have it coming up an example. Let's just get up to that example. So the periodic extension idea, though, I'll just try to explain it by standing in front of you since I can't draw on the screen. Those watching, wait till we get to the example if you're watching the video. The sequence is here. Once we inverse DFT, that sequence from the frequency domain points, it'll plop right down here, but it'll also plop down here over there. It's just like when you learned about Fourier series, it was always for a periodic signal. So the way the DFT effectively works is it's blind. It's got blinders on. It says your sequence has n points. If it actually is a much longer sequence, but you only give the DFT those n points, it forgets about anything outside that interval because it never captured it right. So when you go to transform it back to the time domain, you only get those n points, and then it thinks there's periodic extensions surrounding it because it never was given that information. Another thing about the DFT is you can put it in matrix form. We're not going to do that, but put this in the notes here because this explains some of the properties of the discrete Fourier transform and the fact that you can invert the matrix. And this actually led to some of the early developments of fast and efficient algorithms for doing the DFT. And we'll get to that in the latter part of this section on the FFT. One of the things, though, that if you just take this as being a matrix, if you're going to multiply by a matrix times the sequence of n points in a vector, there's n squared operations in doing that. So that is, and they're complex operations. So multiplies and adds going on there. So that is what we have to beat down when we come up with an efficient algorithm. How do you do that? And I'll go through that in a little while here. This is one of the truly amazing things that some people reinvented around 65 time frame, but was actually invented around the turn of the last century, around 1900 or 18 something or another. I'll explain what I remember from that, but the FFT is in the community is, I was at a conference when it was celebrating its first 50 years or something like that. It was like, it was celebrated at this conference because it was such an important discovery. Not like other discoveries that you know get more airplay. But let's just see how the DFT behaves. And this is going to be a sequence that is got L points of 1s and 0 elsewhere. So we're going to assume that N is greater than or equal to L. So the DFT is going to have N points in it. It will always cover the interval where the signal has support. So we just compute that, and we know that the Fourier transform is going to be this alias sinc function that we learned about a long time ago. If we let the DFT operate on those points, we'll have something like this. So suppose initially we have N is equal to L. And here, for those of you on the video or those of you in the classroom now, here's the periodic extensions. The dots are signal relative to the 10 points that we're going to calculate the DFT on. The open circle dots or stems are the periodic extensions. So immediately when we define our sequence to be 10 points long, and that's going to be the DFT calculation interval, we automatically have to acknowledge the fact that these periodic extensions are here. And when we go through that calculation, the fine dashed line there is what the true Fourier transform of the 10 points is, but from the DFT's point of view, it thinks we have a signal that's a constant. The whole interval with the blinders on is a constant, and it says in the frequency domain I'm going to get all the spectral information is going to be right at 0, and then it will come back again at 2 pi, and so on and so forth. All the periodic extensions on the DFT points, that's what the tilde there is for. So, first big conclusion is if you do the DFT of a sequence with too few points, you'll lose spectral detail. It's like, well, how could I do this better? And data is important for the DFT and FFT. So N is equal to L is not going to work good for the constant signal. If I go ahead and say double the DFT length up to 20 points and just have my signal fill in its natural values of 0 above that, now it starts being able to get some intermediate points computed because it's seeing this more or less like a square wave or a pulse train that's on for 10 points, off for 10 points. So it's now looking like we're sampling the spectrum, because that's what the DFT does, at the peaks and the valleys of this alias sinc function. Is this making sense? This is a progression. It's like I start by just taking the bare minimum, nothing exciting in a constant, so I get a constant. In the transform domain, I just get everything at DC. I double it, I'm starting to get more detail. If I was to zero pad this sequence out to, say, 80, which is what I talk about down here, then I will start filling in more and more points. So this starts to look nicer. And the spacing between these points is always 2 pi over 80, or 2 pi over the length of the DFT. In this particular case, I'm starting for the signal of interest, which is a 10-point sequence of 1s. I'm starting to get more detail, and if I keep going up and up and up, I'll get more and more detail on the true spectrum of that pulse, that isolated pulse. Is this making sense or believable? Right now, there's nothing super mysterious about it, except that if you don't give the DFT enough points, it can't faithfully give you an idea of what the true spectrum is. This is just a summary of all the Fourier transform representations in your life so far. Continuous time Fourier transform, Fourier series for continuous time waveforms, discrete time Fourier transform, which was back in chapter 2, a Fourier series, which we didn't actually cover. Instead, we just went right to the discrete Fourier transform. Really, the differences between the Fourier series and discrete Fourier transform are just terminology differences. It's the exact same calculations involved. So ends your history. This is where we are today. You started way up high in circuits and then came down. So it's your Fourier transform legacy, if you want to call it that, or whatever the right term is. So what are some neat properties of the DFT? First off, if you want to consider linearity, you have to do the DFT over a sequence that corresponds to a common length. If you have a length n1, length n2, but the two sequences, you have to put them on a common length, which means you might zero pad or truncate, depending upon how you're wanting to set this up. A more common approach would be, say, one is a 10-point sequence, the other is a 20-point sequence. I would zero pad the 10-point sequence up to 20, and then work with 20 points when you add the two sequences together. Now, when I say you've got 10 points, it doesn't mean that those, if you had 20 points between here and here where my hands are, and maybe the 10 points is here, maybe it's here, maybe it's over there, so you zero pad all the in-between points. In MATLAB and in Python and in Julia, when you use the FFT, it actually gives you that option of zero padding from the get-go. And I'll just slide over to that for a second. My Jupyter notebook is not working well because of some patches I put on it. It kind of goes away on me. What I mean by goes away, if anybody else has experienced this, you're working in the notebook and all of a sudden all the cells just start to disappear. It's a problem that the notebook is not gone, it's just the displaying is messed up, and they've revved it a few times in the past 2 weeks, and I put on the patches, and it seems like it's still there. I feel like what I have to do is rebuild my virtual environment and just go back to an older version. Doing the notebooks, though, in VS Code is working fine for me. It's just the idioms of the VS Code environment are a little bit different. So this little comment in here is just when I import all of NumPy, which is what the star is doing, I get the top level NumPy modules. So one of the modules that's in NumPy is FFT. So if I do that, these are all of the functions that are under the FFT module. So probably the most common one that we would use would be FFT, and then if I type FFT in there, then I can explore the FFT. So I can do things like pad it if I want to by putting in a second argument. So I might decide to pad it, and I think, yeah, I've got an example of that right down here. So let's just take a look at that. This is pretty similar to what we just did. I'll create a sequence of ones. Do I want to do this right now? I'm going to get into this later, but I'll just show it to you right now. The DFT is the direct algorithm. The FFT is a faster version of it. So in Project 2B, or the new Project 2, I actually have you use time it. I think I've had you use time it earlier, right? What was the problem where I had to use time it in the project, right? Okay. So there's two types of magics that are, and that's what the commands with the percent signs are called in front of them in Jupyter. This is called a line magic, and if I put 2 stars in front of it, or 2 percents in front of it, it's called a cell magic. So I have you use that in the new project too. So at any rate, let's just first go with this guy. Here I'm just going to have it padded up to 100 points. It starts off at 10, but I'm going to pad it up to 100 points. So it's just computing, using time it, it's averaging, it's doing a bunch of repeated experiments to come up with the time it takes to do that FFT. And I didn't practice on this, and it's probably going to take longer than I want. There's the answer, though. 27.8 microseconds. It ran way more loops than I wanted it to, but it's a measurement. But let's just give an idea. 27.8 microseconds. If I pad it, the second argument lets me pad it up to 1024. Let's just do it like this. So we're going to pad it up to 1024 and rerun that. Okay, 57.3 microseconds, not really that much longer than it took to do 10 or 100. But let's suppose I take this to 1023. Kind of remember that, 57.3. What do you see? It's about double. The FFT engine behind Python, and I think in MATLAB and in Julia, it's called FFTW, fastest FFT in the West is what it stands for. And it was invented in Texas, so they always say they're the West, right? We're west of Texas, but at any rate, it's just a thing. So 1023 is not an efficient value for the FFT. I could pick even other values that might even be worse than this, but the FFTW engine takes this and it says, do you want a 1023 point transform? I'm going to try to search into my deep recesses of its brain, so to speak, for the FFTW and try to get you an efficient one. It might be a product of some prime factors or something. Actually, isn't it 1023 a prime number? I don't remember. I'm not going to go down that path, but at any rate, it tries to figure it out. I don't think it is either, but it isn't.
It should be divisible by 3.
Yeah, that's what I think.
3 yeah, it adds up to the 6. Yeah. It's divisible by 3.
Oh, I shouldn't have done this either. Probably not going to be able to get me an answer. Oh, I didn't want LCM. I wanted, what's the other number? I don't,
CF, highest common factor.
I'm just going to forget about that for right now. But at any rate, let's just now take this X1 we had up here of 10 ones. Just let it compute the FFT once, 0 padded up to 1024, and then I just ran, or I'm running the cell again. It was already run, but there's our spectrum. And of course, it's got the discrete points on it, but they're very finely coupled together. So all this semester we've been using FreakZ a lot, and FreakZ uses the FFT under the hood. It takes the numerator of our, which is in our B polynomial, FFTs that, and it FFTs the denominator, 0 padded up to some length, and then it forms the ratio point by point, and then you can have a complex number that you find the magnitude and phase and so on now. Come back to this a little bit later. So linearity applies. You just have to bring the sequence links up. Circular shifting is a little bit different animal. Because now if we want to visualize circular shift, we look at what happens if we take a sequence and shift it by m samples. We know in the discrete time Fourier transform, that's an e to the minus j omega m. When we go to the DFT domain, it will be this relationship, that the shifted sequence x1 will be the unshifted sequence multiplied by w sub n to the mk. So to go prove that, we can make this substitution and see what this w sub n to the mk does when it's stuck inside there. What is it making x1 look like relative to x? We see that when we take this and combine it over into here, we get a shift of n minus m. But because we're periodic or periodic extensions in our sequences, what happens here is that if this is our DFT interval and we want to shift by, we consider the periodic extensions now on the sequence, and if we want to shift it, we're actually rolling the entire sequence with the periodic extension. So if we roll over by 3, we slide this over and some new values slide in from the left, and those are those guys, and then the ones that we keep have just moved to the right. So we can move it backwards or forwards. And if you remember, and this has showed up in the past in some of the homeworks or some of my code under the hood, I use Python's roll function. Python has a function called roll, and what it does is it rolls it off, brings it back again around to the end. So another way of thinking of the roll operation is thinking of it on a cylinder. So if you just click it around, the knob around, you're rolling stuff back in from the opposite end. Everybody good with that? That's one of the things of the DFT. This is actually the way you can shift frequencies if the DFT points are in the frequency domain, which they are, and then you can implement a filter that's frequency shifted. That's the way the channelizer or filter bank function works for the project 2B. This is just an example of doing this in Python. So I put in a sequence that has 5 1s and 3 0s. I don't use the roll function, but I instead go through and FFT it, or inverse FFT it after I multiply by this e to the minus j 2 pi n over 8, and that's going to shift it with a positive value, so it's going to rotate it back to the left by 1 sample. So then when I IFFT it, I get the sequence shifted to the left by 1 point. Okay. There's a duality property which just says there's a direct relationship between the two domains. You just have a scale factor of n, and then you have the modulo property again. So this just tells you that if you want to look at the sequences back in the time domain as DFT points, you can do that. You just have to take into account a minus sign and a scale factor n. And this is useful because it tells us that the DFT, or an FFT, which implements a DFT, can also implement an inverse DFT just by conjugating the results and scaling by n. And we'll see that when we're looking briefly at the flow graphs for the FFT. There are symmetry properties. The fundamental symmetry property that I really want you to be aware of is that if x of n is real, we get this result here. It just says DFT point k has the same magnitude as DFT point n minus k, and the angle is the opposite. This is just the same idea as the Fourier transform of the sequence, except it's at the discrete points. A new thing is circular convolution. We know about linear convolution. We know that in the Fourier domain, the DTFT domain, is a product of the Fourier transform. So working this backwards, what does it mean to multiply the DFT points together here and then inverse DFT that? What does that get us? Well, what we're going to get if we consider the periodic extension, we know it's going to be a convolution, but it's not a convolution that's void of the periodic extensions. It's going to be a circular convolution, as it's called, because these two values in the convolution sum are going to be the periodic extension version. So when we're shifting the sequence, we're actually rolling it left or rolling it right. And we can get a handle on that by going through an example. This is just what it looks like, though, if you plug it in. In other words, at the top here, I'm just going to plug in that product, and then I'm going to plug in what x1 is in terms of the sequence, and then plug in what x2 is in terms of the sequence with some offset factors, and then it shows you that it is the so-called circular convolution. So the book likes to use this notation, an asterisk, which we used for convolution, but then they put a circle around it and put a subscript n, and that means it's a circular convolution based on an n-point sequence. So this is the idea of circular convolution, and whether or not this shows up on the exam, we'll talk about that later, but suppose we want to see what the circular convolution is of two sequences, just to go through the time domain version of it. In actuality, if you wanted to do this, you would DFT both of these sequences, multiply their points together, and then inverse DFT. That implements the circular convolution. But just the exercise of going through the circular convolution all in the sequence domain is we have to take the first signal as x1 of m, and then the second signal has to be circularly shifted, and that is what I've displayed here. If we start off with this sequence is 1, 1, 0, 0. When we shift it to the left by 1, we're going to get 1, 0, 0, 1, because we moved it to the left by 1, and then we multiplied the blackened stems together and add them up, and we get 3, and work that all the way through. That would be the circular convolution worked in the time domain. I'm not a super fan of having you do that on paper because it's like it proves that it works. It's just a tedious operation. The whole reason why you'd want to understand it, though, is because you want to learn what's going on in the, what do you have to understand differently if you use the DFT/FFT to do the convolution. And so here I just did it straight up. I multiplied the DFTs together point by point, and I did this all as a hand calculation, multiplying it out, then getting the individual points, doing the same thing for the second one, multiply the points together, get these 4 points, and then inverse transform that by evaluating n at 0, 1, 2, and 3, and lo and behold, I get back 3, 4, 3, 2, which is exactly what this got, 3, 4, 3, 2. And of course, there's actually symmetry in here as well. So how to tackle the time aliasing problem that the DFT gives you when you try to use it for doing your convolutions in the transform domain. If we didn't care, we would just skip this subject entirely, but this is one of the big things about using the DFT. You can do the filtering in the transform domain. So how do you tame the DFT so that the aliasing is not a problem? And this is just some pictures about how that works. we want to understand how can we set up x1 and x2 in the circular convolution so that we don't have aliasing. So we know for linear convolution, one signal, the other signal flips, we slide it past, and we compute the convolution, and we know that we're going to get at most L plus P minus 1 points when you do a linear convolution. So how are we going to make the circular convolution, implemented in the transform domain, of course, behave like linear convolution so we can use it as a filtering operation? So I'm going to kind of go with my pictures, which I created, I'll say decades ago now, because I've been using this for more than 20 years. Just take x1 and x2 of n minus m modulo n and just put up all the periodic extensions. So these are those two signals. So now I'm going to slide this one past the upper one, and you can see whenever the gray cells are crossing in, maybe my pen has started to work. It hasn't. Maybe the battery actually went out on me. But the battery's gone. I do have more in my, oh, there it goes. And Dell has asked me probably about 5 times since I bought it at the beginning of the semester, are you happy with your purchase? When it works, I'm happy. When it doesn't work, I'm not happy. This cost me $30 because my old one died. At any rate, when you're doing the circular convolution and trying to make it emulate linear convolution, where those two red lines are, that's where we're interested in the action. As we slide this one past the other one, we're seeing that we're going to get aliasing with respect to the output because we have some of those periodic extensions that'll slide through. In other words, when this point right here finally engages over here, we're going to have a lot of gray area in here, which is also going to clutter things up. So what I do, I expand it as a sum of linear convolutions, but that's where the time aliasing occurs. So these are the dominant terms that matter when I'm trying to make the linear circular convolution behave as linear convolution. So it's this terms, it's this term right here that is the bad one. This one right here occurs outside the interval. This one occurs before the interval. So it's in the interval that runs from 0 to n minus 1 effectively. It's this one that we want to mitigate somehow or another. So what you do to mitigate that is you take the sequence you're trying to convolve and pad it with zeros. So you pad x1 with a bunch of zeros, and then you pad then you pad the other sequence x2 with a bunch of zeros. And then what will happen is, in particular, this is the r is equal to 1 term. You can see that it won't interfere at that point. If we pad enough zeros on the end of x1 and x2, this term right here will not contain any values. It'll be all zeros due to the padding. So to see how that works, I'll just do an example here on the computer. I'm going to do it in just what shows in the notes here. Linearly convolve a rectangle with a rectangle, and I get a triangle. So here, if I don't zero pad at all, just keep the sequences, the DFT length at 6, the sequence lengths individually are 6. What happens in here, this term right here is the term that I'm looking for on this interval 0 to n minus 1. But it's this term right here. This was our term called r is equal to 1 from before. That will combine, and it totally garbages up the final output, the sum of these. And that ends up making it look like a constant. But it could be anything. It's just not what we're looking for. It's full of time aliasing. If I choose n to be greater than L plus P minus 1, and this is the thing to remember about circular convolution. And if I ask you a simple question on the final, like what do I have to do to avoid time aliasing in circular convolution, I just make I just zero pad such that the total length n is L plus P minus 1, greater than or equal to that. And here I drove it right to the limit at 10. And you can see that this second or third row down here, it's clean. Well, I didn't draw that right, but this whole interval is clean. And that's because of the zero padding. Sound good? I mean, this is just the property. So which came first, the chicken or the egg? I mean, in the case of the DFT came first from a spectral analysis standpoint, and then they said, oh, what can we do in the frequency domain for filtering? And then they said, convolution is going to be all garbaged up because of the circular convolution idea. But then they came along and said if we zero pad, we can make it emulate linear convolution, and then we can build a filter that way. There's a few other properties. These are all in your tables that you can have for the exam, of course. I'm not really going to focus on this. It's just kind of the standard stuff. We've just been drilling on this one, though. And because of the duality property, we can multiply in the time domain, and then we'll just be circularly convolving in the frequency domain. And this looks like the windowing theorem from before, and in fact it is. It's just a discrete version of it, the DFT version of it. So we can take this idea of circular convolution implementing linear convolution, and we can just go through a more detailed example. And I'm just going to look at the picture here. Is we will zero pad. This is the rule then. We want to get L plus P minus 1 as our total length. So we put in P minus 1 zeros, L minus 1 zeros here. We endpoint DFT them, multiply them together, and then inverse DFT. This is the basic filtering operation in the transform domain. And when you first see this picture, the thing that should kind of worry you some is the fact that we have to do 2 forward transforms and 1 inverse transform. And you could say, how could that be more efficient than just a linear convolution? It happens when you get large sizes and the DFT is replaced by the FFT. So is that believable? I mean, divide and conquer, so we're going to get the DFT very efficient with FFT algorithms, and then we can make it such that the cost of doing 2 DFTs and 1 inverse DFT can be less expensive. And in fact, if the filter was pre-computed, this would be done once and stored in memory. So these DFT points would just be sitting there already computed. So you really just have 1 forward transform and 1 inverse transform. And that's what the channelizer block does in Project 2 new, or Project 2 option B. So I go through a more detailed example in Python. It's just sort of the same thing with getting the zero padding enough. Probably the next interesting thing, though, is what happens if you have an infinite duration sequence. So if they're both infinite duration, I don't have an answer. But if the filter is finite length filter, an FIR filter, and I want to filter an infinite duration sequence coming in, what you can do is this. You can suppose you have this situation where your impulse response is finite and your sequence is running forever. Think of the software-defined radio example I was going through last week, really long record of samples. I think it's the vector that I put into Slack is 35 million points. It's 30 seconds at over a megasample per second. Filter coefficients here is just 7 points, but it could be longer. In that project 2B, it's 355 point or tap FIR filter. But at any rate, what you do is you segment. So you segment this input sequence into chunks and have it do the transform domain convolution on those chunks. And again, just sticking with the pictures, if I do this operation of my sequence and I zero pad it so that linear convolution can be implemented with circular convolution with no aliasing, then what happens is I come along and I filter each one of those chunks in the transform domain and then inverse transform it. I will get a little piece at the end that hangs off and got filled in because of the action of the linear convolution stretching the signal out. But in this case, this is an overlap and add kind of a strategy where I take that overlap, keep it, and then add it in to the beginning, and it puts it back together. This is what runs off the end, and it gets added on to the beginning of the next one. There's an overlap and save approach as well, but this should be satisfying that we can play that game. I don't know, it's amazing, but it works, and that's project 2B. It does exactly that, except I have multiple filters. I take the original filter and just roll it to get it centered at different frequencies, but then it can do a bunch of channels in parallel, but it uses this very exact idea. Okay, now we're going to transition into computation. So the DFT topic is broken up into what it is, what are its idiosyncrasies, what are some uses for it, and then why we love it so much, because we can make it computationally efficient. So that's this next topic, and yeah, we have a little bit of time before the break. So the direct DFT looks like this. We have endpoints. This could be complex. This is always complex. So in general, endpoints requires n squared multiplies, and in fact, they're complex multiplies. So a complex multiply each requires 4 real multiplies and 2 real additions. And a complex addition requires 2 real additions. So we've got a heavy workload going at us, but we have an approach to do that. And the guy that first came up with this, his name is Schuster, I believe, and it was 1870s, 80s, or 90s, somewhere in that time frame. He was a scientist. He was studying sunspots and the periodicity of sunspots in time. How he got into all this stuff, I don't know, but he needed an algorithm that he could do to get the spectral lines associated with the periodicity of the sunspots. That's as much as I remember it. I may have the story kind of garbled up, but he wanted to be able to do the calculation on paper because he didn't have a computer, right? And he needed to efficiently take those data records and compute the spectrum, and that's where his need for the FFT came into being. Now, it went kind of unnoticed for a long time, and then it was in 64, 65 time frame that two investigators, one from IBM, and I think the other one might be IBM or another company, but the people that get the credit for originally had the credit for inventing the FFT were Cooley and Tukey, and it was a radix 2 FFT that they invented. They later acknowledged the fact that somebody else invented it earlier. Is that believable? I mean, before the age of a computer, somebody actually had written it out. How did they figure those things out? I don't know. Some people in library science like to go look for stuff. I wouldn't do it. Why wouldn't I do it? And probably why wouldn't you do it? You're charging forward. Solve your problem, get your customer happy. You're not going to go look back in time. But you may bump into it if you start reading stuff. But I don't know, going from 64 all the way back to 1890, looking in books and journals and stuff seems pretty hard. I usually look back just a few years, 10, 20 years maybe. But at any rate, this is truly a divide and conquer, and it's an amazing story. So I'm going to go through this, and then we'll take a break. I'll go through this briefly. So the origin of the radix 2 algorithm, as recreated here, is just to say for whatever reason, somebody said we're going to do the DFT, but we're going to DFT over just the even points and DFT over just the odd points. So what that does in the sum is you index it so that you're stepping over the even points here, and then you're stepping over the odd points with the second sum. And of course, the number of terms in the summation is adjusted to be exactly n over 2 in both cases. So the assumption with the radix 2 is that n be a power of 2. So like 4, 8, 16, and so on. 1024, 512, 2048, 4096, etc. Those are all values that most of us are familiar with. So this is the beginning of what is going to happen. Even points, odd points. Then you make the observation that there's a w sub n to the 1 that's sitting inside of here times k, and that is not a function of our sum index, r. So w sub n to the k factors out in front. And what else is going on here is that we have w sub n to the 2r sitting in here. So w sub n to the 2 ends up being just w sub n over 2. And this probably is the fundamental discovery was right here. This factors out in front, but then what we're left with is w sub n squared, but w sub n squared is just equivalent to w sub n over 2 as a factor. So now the twiddle factors there's less of them because we're now reducing down to just n over 2 of them. So when we go ahead and put this together finally and use that factor that came out in front, I call that the combining factor. So we combine, we have an n over 2 point transform combined with another n over 2 point transform, one over the even, one over the odd. We combine them and we end up with this sort of an operation. This is the block diagram / flow diagram. So we have an n over 2 point DFT of the even, n over 2 point DFT of the odd, and then we have the combining algebra. So that's what it's referred to as. We bring a point from both DFTs together to form the n-point DFT. So if we redo our calculations on computations, for an n over 2 point DFT, we have this many multiplies, n over 2 squared, and we have to do 2 of them. And then we combine with n complex multiplications in general, and then the additions is similar And you can see if you plug numbers into that there is a savings, a small savings, but there is a savings in doing this, just because of the way numbers work out. N squared over 2 plus n is smaller than n squared. I can type it in, but I'm going to show you a table. Is this believable? I mean, this is just step 1. Step 2 is to do it a second time. So now take the n over 2 point transforms into n over 4 point transforms, repeat the operation, and now we have something like this. We have combining algebra for the two n over 4s, and when we finally take, say, an 8 point transform down, we've got a 2 point transform, which is right, there's 4 2 point transforms, and then there's the combining algebra for the 2 point transforms into 4 point transforms, and then finally there's the last combining algebra to go with the 2 4 points into an 8 point. And all of the calculations look the same. They're all referred to as a butterfly, and they're referred to as a butterfly because you have a straight through upper and lower, and then you have the cross point. So it's supposed to look like a butterfly with wings. That's the terminology that I learned a long time ago. So an endpoint transform decomposes into nu equals log base 2 of n stages, and then the number of multiplications and additions gets evaluated, and this is after 2 stages, but in general the result is finally multiplications is n over 2 log base 2 of n. And that's because we notice in the general radix 2 butterfly that this multiplication can be pulled forward in the flow diagram to be just one complex multiplication, and then there's a sign change. So there's this -1, which doesn't really require any multiplication, just changing a sign bit, let's say. So immediately, though, when we go to a 10-point transform, we're at about 10,000 computations, whereas direct, it's about 1 million. So that's a huge savings. That's over 2 orders of magnitude, or about 2 orders of magnitude. The other thing amazing about the DFT in the radix 2 FFT is that it's an in-place calculation. As you go through any butterfly, these points and these points directly carry forward from the 2 input points. You need a temporary slot, but you can, when you finally calculate this, you'll have a temporary, but then you'll be able to write over it in memory. So you don't have to create a whole nother array to store the results in. The one thing that's tricky is you have to introduce bit reversing because of the way the even and odd works, say for the 8-point transform. This is the order that things go in at, so it comes out in normal order. And bit reversing is just noticing that if I put the 8 bits into the 8 points into the 3 bits that correspond to it, I'm just flipping the order of the bits. So in logic, or how you put it all together and address things, you're just flipping the bits around to get the order reversing going on, or to get the computation set up. So this is a table just showing you the improvement factor, and we were looking at 1024. It's about 204, so that's over 2 orders of magnitude. Here's an FFT in C that I've used in the real-time DSP class. I didn't invent it. It's just a published one. There's a second algorithm that's just flow graph reverse of the decimation in time. It's called decimation in frequency. I'm not going to go through it here. I'm just going to get down here to the end, and you can see that the decimation in frequency algorithm puts things in normal order. Things come out in bit reverse order, and this flow diagram is just the flipped over version. Remember network transposition from last week? So that's pretty cool. And duality property is what tells you how you can calculate the inverse DFT from the DFT of 1 over n, and conjugation goes in to do that. So that's also pretty nice. So the FFT I showed you in C has that built into it through a switch, and it can switch between inverse or forward modes of operation. So now we're down to a little bit on applications. Don't have a whole lot of time. I'm going to stop though right now and come back and kind of assess where I want to go next to get us done and get out of here. Talk about all the things that only one person heard, right? You can testify. I went through it though. I said we're going to come back when everybody's here. So let's take our break. Do you want 10 minutes or do you want 15?
15.
You want 15?
Yeah.
You want your coffee, but you got it.
Oh, 15.
Oh, okay. Okay, go get it. Come back at 9:30. The projector hopefully will die in that interval, and then I can restart it. So we're getting ready to get started again. Just one comment about the jury duty. When I did finally get done, immediately when we made our decision and we went in front of the judge, Colorado College had some pre-law students that were attending the courtroom trial I was in, and they immediately came into our jurors room and they started interviewing us, asking us, how did you come to that? They were just curious. They made me think we didn't come to the right conclusion because they thought, how could you have come to that, guilty verdict? But I had a solid understanding, and I just had to help convince a few other people to think of it that way, and then we eventually got a unanimous.
Never talk to lawyers or would-be lawyers.
Yeah, well, they were going to grow up to be lawyers, I think. Colorado College is a pretty rich kid school, I believe. Okay, so I wanted to go look at a couple of applications, but not really a lot. There's a lot of games you can play with the DFT, and one of them is, I already alluded to this, if you're doing the DFT of 2 real point sequences, you can do it with a single FFT. In other words, you can interleave the real and imaginary parts to form a complex signal, and then you can separate them out at the end. So this is how that works. You would separate out in the inverse transform if you wanted to do that, play that sort of a game. Another game you can play is a 2 endpoint sequence can be calculated using a single endpoint transform, again, if it's real. So this kind of explains how that would work. And this is really no surprise because it's kind of like the start of the DFT, the radix 2 algorithm itself. And then we have what's in project 2 new, or 2B as I've called it, the overlap and save filtering, and then there's an overlap and add, but I've implemented the overlap and save. So we were talking about this earlier, but this is how it's mechanized in software to always do 2 endpoint transforms, and I talked about this last week a little bit, and then in this case, rather than adding, you're saving. So you get at the output always some stuff that's got the aliasing in it, but you only save half and put that into the output. And then you take another set of points at the input. And in the case of the project with the channelizer, these coefficients are rolled either left or right, and when you roll these coefficients, that's taking the frequency response or the DFT of the Fourier coefficients, and that's like if the filter is at 0, you roll it up, it'll be at a higher center frequency. It'll be a complex impulse response. Now if you roll it down, and you can roll it all up and down, and that's, remember I demoed that last week. That's how that project works. That same idea can be used if you let the impulse response be a time-reversed impulse response, as in correlation. So the filter bank can then do a correlation operation, and then that can be used to calculate a complex ambiguity function. And that is also in the new version of SIG-SIF, new, which I include in that zip project. That'll eventually get pushed up. My co-author developer is still working on the files, and there'll eventually be a newer version with some of these updates. So this is the overlap and add, but I'm not going to spend time on that. Actually, these functions, though, have been in the package since the very beginning. There's two functions. There's FFT OS, FIR, and FFT overlap and say OA. So my co-author didn't even realize they were there. I'd forgotten they were there. I wrote them when I wrote the Dummies book, though, is when I created that stuff. So the last topic in this area, though, is spectral analysis, and this can segue right into the review. The idea with a spectrum analyzer is you would come in with an anti-aliasing filter, continues to discrete convert, window it in order to control the side lobe level, and then DFT it. And then you might move on to an average periodogram, which is what our spectrum analysis tools do. So the key points, though, in doing FFT spectral analysis, and this is at the bottom of the review sheet, is this idea right here. To build a very back-of-the-envelope type calculation spectrum analyzer, if you're given the sampling rate and you're asked questions like, what's going to be the resolution of the spectrum analyzer? It's going to be delta F, which is just the sampling rate divided by the chosen FFT level. So this makes for a very simple homework problem in the case of some of those problems, or an exam problem. It's a design problem then. So this right here is probably the most important, but actually, in my mind, they're both important. The bottom one is probably the most important, but that one is a nice design problem because it says you want a resolution of so many hertz, and you've already picked your sampling frequency based on low-pass sampling theory, so solve for n, and suppose n comes out to be 1001 or something like that. You'd say, no, I'm going to make it an x higher power of 2 in order to be efficient for the FFT. So then that kind of tells you how to design your spectrum analyzer. If you want to know what frequency, when you look at the bins in the FFT, and that's what the FFT output is referred to when you're using it as a spectrum analyzer, you think of each FFT point as being a bin in the terminology of spectral analysis. You can figure out exactly what FK is going to be, or vice versa, what K is. So you can spin this around, like if I want to get at point 126, what frequency does that correspond to, or inversely, working it backwards. So if you have a spectral capture, you can do a peak find on it, and if you only have the integer axis, you can create an axis that you can look up the frequencies from. So that's really probably the core basics of spectral analysis. The windowing is done in order to keep the side lobe level down, and we talked about that a long time ago. So here's what happens if you try to resolve two closely spaced sinusoids. If they're far enough apart, as they are here, they're easily resolved. You get them closer together, they start blurring, and then finally you can't separate them at all. So the solution would be introducing a window to help out, but really to resolve two closely spaced sinusoids of the same amplitude, you have no choice but to increase the amount of data in an attempt to get finer resolution in combination with zero padding. So zero padding will also help out in there. because it will evaluate more points along the DFT, right? Windows, these are a collection of windows, but I think we looked at this a long time ago. The synopsis, and this, to me, is not something you need to know for any exams, but if you are using an oscilloscope that maybe has an FFT option on it, which is the reason why I was at Hewlett-Packard. I'm getting confused. Agilent. I keep getting the names confused since I'm working for Emergent, which is now ARCA, but Agilent. When I went up there and did my FFT applications class, they were getting ready to introduce their first digital oscilloscope that had FFT capabilities. Now every scope does that. The ones we have in the lab do that. But this was kind of an understanding taken from a FFT spectrum analysis book that I had, and I didn't keep when I moved out of my office 2 years ago. It was a nice book, but I just had to part company with a lot of books because I had too many. Somebody around here has it, though. Now I've wished at times I had it, but so it goes. At any rate, though, this is the side lobe level, and then this will be the width of the main lobe. So this gives you an idea of how easy it is to blur, how the rectangular has the narrowest width, and then the roll-off rate, and then the equivalent noise bandwidth. So another aggravation issue that comes along, if you're not commensurate with your signal that goes into the FFT, what will happen is you won't have an FFT bin. I guess I can just draw on this. You won't have this situation. You want to see that, but instead you get points either side just because you're not commensurate. You can't control that. The signal is being captured, so you have some error in the amplitude. So this picture shows what's called scalloping loss, and it's just showing you that as you move along the FFT and the bins, as I'm showing you with my hand on the screen, you'll peak and then you'll fall into valleys where you get two values, and then where you drop down and come back up again. It's just a factor of the nature of the choice of the windows, and that's why I guess it's not in here, this table. I was thinking it had scalping loss in here, but I think the book that I gave away effectively had some analysis of that. So let's see, this is just showing you the idea of using windowing. In this case, this signal is available because you windowed, so you have better roll-off rate, whereas if you don't window with only the rectangle, you can't get your hands on that. In this example, I had two signals close to each other of equal amplitude and one signal far away at a much reduced amplitude. So the windowing idea helps. Getting more data always helps. I mean, you can always use more data, but in some applications you can't get it. So is that your life? If you're a signal processing person, it's like, give me data. What do they do for me at work? I now have a server that has like 50 cores in it or something, and I'm repurposing it to run simulations. So I SSH into it, and I've got jobs that are probably finishing up right now. But my team recognized that my stand-up a few days ago last week. They said, hey, we need to get you a machine that you can run your simulations on. And they came through, and VS Code has a really nice feature. If you haven't used it, it's called, the extension's called the SSH remote plugin. It works nicely.
I did that with Dr. Computer. He does computer arts.
Okay.
He created his own, I guess, network where we can go code, simulate, and then share. So he does not have to get the files.
Does not have to get the what?
Get the code, because we can do it in his environment.
Oh, okay.
access to his environmental,
Who is that in computer science?
um,
So you took some CS classes?
no,
Okay.
it's an ECE class.
Oh, okay.
No, not Pereira.
At any rate, I just got off on that tangent, but what I want to say, I guess I don't have that in here. FFT spectrum analyzers for random signals, that's covered actually in a separate chapter, and I'm going to not spend time going through that, but that does get utilized in the project. I wrote yet another PSD function that's going to be included in the new SIG-SYS module, and I have you use it if you work the channelizer problem. You get to set a calibration mode, so it calibrates to display accurately for sinusoids or accurately for noise. And since I'm doing that, and since I'm going to go do that right now, I'll go over and take you on a tour of that. This is just part of Project 2B, but I'm just showing you how I now have this new spectral analysis capture function. So it's PSD, but PSD now has another mode in it where you can put an optional argument at the end to control whether or not how you want to have it calibrate for noise or for sinusoids. So here I use it to do a spectrum on the channelizer to look at each individual channel stacked up on noise, but if I'm doing it for sinusoids, which eventually happens down here, then I set a mode in there called false, and so it now attempts to get this to represent a dBm level if I knew that it was 50 ohms or something like that on the signal. It doesn't change the content of the FFT or anything like that, or the average periodograms. It just changes the scaling because I decided what I did on exam 2 was try to make you learn how to do that, but I decided it'd be better to just have a function where you could just have it manage it for you. Why do I care? It's because I'm using Python so much lately at work that I'm just saying, hey, I should make things more flexible. So at any rate, let's go back over to the notes and look at the review. Or should I look at the histograms? Let me look at the histograms first. Unless you want me to go through the exam, which I will do. I think I put the solutions out last week. You can look at it now that I've given you your papers. You got them back from me. And then we can look at things if need be on Slack. How would that just take care of that, get that off the table? But I do want to go through the class standing. So I didn't grade 6 yet because that's a long thing to grade, but it's kind of normal. So using sets 1 through 5, here's where we're at histogram-wise at this point, normalized to 100. We've got one person maxing out because bonus problems and stuff right at 98, and then a low at around 85 point something or another. Merged together the two exams, and the exams have not done as well as I had hoped, but they are what they are. They're data. You know, I have data, so this is what the exams are. One person's average is, well, this is exam 2, was around 95, and then we had some lower points and score values in here. If I compositize everything, and I do have my spreadsheet numbers here, everything together as we know it today, so in other words, the 5 homework grades weighted at 25%, the 2 exam scores each weighted at 15%, and then divide by the number of weights, points, which would be 0.25 plus 0.15 plus 0.15, then this is the histogram that I'm able to generate from that. So I call that the pre-average. What's going to happen as I start bringing in the projects the last homeworks, which are generally pretty easy and everybody gets all the points on those, everything's going to move up. So I know that's going to happen, but you want to hear me say, what would I do today? If this is what I had, what would I do? I would probably give some A's, and I'd probably give an A- or a B+, somewhere in that neighborhood. But I don't know exactly. I mean, I don't like seeing numbers 80 to 90, and I don't want to have to make a decision because I want to be in denial right now. I just want to say, no, it's going to get better, and I know it can happen. So that's my thought on it right now. I'm not out to, I don't see anybody that's going to get a C or lower if you're a graduate student. I just don't know whether it's going to be B, B+, A- or A. It's going to be in that range right now. Everything's pretty much within striking distance. If you just look at the numbers that are still out there, there's 55%, 0.25 plus 0.3, so that's 0.55. So that's 55% of the grade is displayed in these numbers. There's 45% more data that'll come in, and that can create a huge push on all of that. So if you want to know what to do to practice at how your exam average will come out, you can just take a guess. I'll give you your number right now the way I have it recorded, and then you can say, if I get this here, add it in, and then see where you shift to. I know it's going to come up here. One of the things you can do to really discourage me, though, is to just not do anything and then do poorly, and then for me to just say, hey, what do I have to do? So it's within my control to do what I feel like is the right thing to do. Because the idea is the grade is not what really matters in the end. It's what you know and what you can do with it in your work. It's reflective, but that's kind of where that's at. So any questions that you might have for me?
On the homework that's due on Monday, it says 4 required, but there's 6 questions. Does that just mean we have to do 4 of the 6?
Yeah,
okay.
Exactly. I think I'll let you have bonus points if you do more. Don't I say that?
I think so.
Yeah. See, that's going to help boost you up too. The person that has their homework average really high is a person that's gone for bonus points. So it works because that's an overflow, and that's how come it's very easy to get close to saturation on homework. And I'll consider if it goes over 100%, it's been like 101, 102, 105 in the past, I might let that just ride through. Is that okay? Nobody complains about that, right? Or should I invoke saturation and let it clip at 100? Okay, so that's done. Let's go over and look at final review. I'm going to hope that this will work for me. So I changed a few things in here from what the old 2018 one was that I had posted earlier on the website, but most significantly is I put some red highlights in just so things would jump off the page more. First off, the exam is comprehensive, but there is new material, and that will be emphasized more. It'll be about 5 pages. I think all my old archive exams are exactly 5 pages, so why should I make more trouble for myself? Why did I create a new project this semester? I shouldn't have done any of that. But the reason why I did that, honestly, I wrote that function for the new updates I was putting in SIG-SYS module, and I decided, hey, I should do something with that because I wanted to get motivated. And I actually made that whole function much nicer and better as a result of all the sweating I did over the weekend. When I thought things were going to totally cave in, I just kept doing like I always do. I set it down, came back, and just kept pounding away until I finally kind of got it all massaged into the right way. So I'll be happy with that, and my co-author wants to learn about channelizers, my co-developer for his job, so he's going to benefit as he merges it into the new release. At any rate, that just shows you how you can take on some new things at the end, as crazy as it may seem. So it'll be open book, open notes. We were going to talk about this today. What do we want to do? I will bring a book in, a paper book, because some of you have electronic. If you have a paper version, I'd like you to bring it if you can. In terms of the notes, did any of you make paper copies of the notes?
I will print them out, but I haven't yet.
You will?
Yeah.
You can collect money from anybody else in the class.
Yeah.
Are you going to share them, I guess, is my next question.
I was gonna put sticky notes on them.
Okay.
For each section.
Okay. When I retired 2 years ago, I had a notebook that a student left me with that it was exactly kind of set up like that. He said, here, you might need this. He gave it to me at the end of the final exam. I'd really like it. If not, I can burn paper, but if you're going to do it, I'll even, I'll put some money into, and the rest of you, if you feel like you want to help grant out. Is that good by everybody? I don't know what your approach is going to be for as you work through the exam, whether you're going to want to look at the notes, whether you're going to want to look at your old crib sheet and a new crib sheet that you might have made for exam 2, and whether you want to look at this review sheet, because there is some material at the bottom of the review sheet on spectrum analysis.
Cheat sheet.
Oh, yeah, definitely. You get all that stuff, so.
By that I mean, are you going to bring it, or do you want us to print it and bring it?
I want you to have your own copy of it. Yeah, you might like this stuff at the bottom, because this pertains to the spectrum analyzer thing I was going through. It gives you kind of a little overview of what's going on. Okay, so we have that settled. We talked about this at the start of class. This is the exam schedule. We're 8 to 10:40 class time, so we have between 8 and 10 to do it. Most of you have not been able to get here at 8 o'clock. I'd really, really, really like you to come in at 8 o'clock and go for it so you can get out of here. I will, if you come in late, just be quiet and get to work, but 10 o'clock is our cutoff time, so be respectful of that for sure. So, open book, open notes. So the rest of this is just a review of things. Basic signal types and properties like rectangles, triangles, other step functions, deltas. Something will be woven in, whether it be a convolution sum example problem or something like that. When I say likely, though, I'm not saying absolutely for certain, but it's likely. I mean, things that are favorites of mine, things that I think are good standards that may, something you saw in an earlier exam. If it's something that I think is foundational. No classical solutions to LCCDEs. I led you through that torturous path already, but you have it. Yeah, you can tell stories about it. DTFT of systems. It just sort of weaves itself into a lot of problems. So not a specific problem on properties or theorems, like you had in an exam, but it'll be useful. It's just part of your bread and butter. It's what I call DSP math. There will be something with the Z-transform. It's fundamental, partial fraction expansion. I consider that to be a bread and butter problem. So I think it's cool if I put one on the exam, because that's something that you've probably enjoyed doing if it's easy partial fraction expansion. Just check that out. So I've already answered that question. Problem in this area for sure. Sampling theory, not a specific sampling theory problem. It might be something like the bandwidth of the signal goes up to 25 kilohertz. We want to set up an FFT-based spectrum analyzer. So you have to pick the sampling frequency. So if I say the bandwidth goes up to 25 kilohertz, you're going to sample at 50 kilohertz, and then you're going to base the design of your spectrum analyzer if you want to get 0.1 hertz resolution, let's say, on that, you're going to take that 50 kilohertz and divide it by that 0.1 hertz, and that will give you a number that you can integerize and then round it up to the next higher power of 2 or something like that. Is that cool? That's what I call the back of the envelope spectrum analyzer calculation. It's the type of thing that you'd say, what am I going to need? How much data do I need? You know, if I'm talking to an FPGA developer and I want them to get me a test vector from Verilog or VHDL so I can play with it in Python or Julia, we can work that out easily. Multi-rate, upsampling, downsampling, and rate conversion, that will show up very likely in some problem. Maybe not extensive, but I'm also a fan of revisiting that because people have had problems making plots for me, and I will give you a page that has, you know, here's the spectrum here, 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 and here. Some people did really good on that on this exam. You know, they did excellent, and some people didn't do so good at that. They were inaccurate either in frequencies or in amplitudes or just showing the full spectrum. So I might say I want the whole interval plotted so I know that you know what's going on there. Likely is all I'm saying there. Or I'm saying almost certain. Random processes and quantization, the most that you would have there, and I don't even have anything written down in there, but you would say something with quantization noise, SNRQ. Get this. It's not working for me. So what would you do with SNRQ? You would just, it might be a question like if my SNRQ is 80 dB, what happens if and I'm using so many bits, like suppose I'm using, say, 14 bits, if I raise it up to 16 bits, what additional SNRQ? And there's an equation in the notes and in the book that just says what is SNRQ. Remember the equation I'm thinking of? They used a few times, so it could be something like that. Not super likely, but it's possible. I mean, I do have the possible over here. General transform domain analysis of systems, time, frequency, and z-domain. That's just works itself in as needed into any type of problem. Likewise, magnitude, phase, group delay, stability, causality, inverse systems, as needed. It's not a really focused problem. All pass systems, minimum phase, generalized linear phase. There'll be a problem on that for sure. There was confusion. Some people in the exam problem did all pass rather than linear phase. They misread the problem or were confused on that, so I'm going to give you another shot at that for sure. And problems I've had in the past on the final exam are very simple. They would be something like bring this up again. They would be, this is an example of the way I like to see if it's a problem with multi-rate. This is the type of thing I'm looking for there. But then if it's minimum phase, all pass, minimum phase, linear phase, it might be a problem where all I'm asking you to do is draw these pictures. Very likely I'll do something like that. I'm not interested in all the detailed math like you had in the exam problem, but it might just be draw pictures like this to know that you have the concepts of how to do that. And if you want a quick review on that right at this moment, does anybody want me to just kind of go through it?
Yeah,
Yeah, okay, okay. So here's the system that has some poles and zeros in it, and we want to decompose it into a minimum phase and an all pass. So we take the original system, and without working through the detailed math, just drawing the picture, we have to take any zeros that are outside the unit circle and reflect them inside the unit circle, okay? That makes it minimum phase. But we have to create an all pass system so that when we cascade the all pass with the minimum phase, we get back to the original system, right? So we move the zero inside. We have to annihilate that zero with a pole, and then we have to have an all pass that has the zero on the outside to match with it. And always, always count the number of poles and zeros. So here there were 2 zeros, or 2 poles at 0 because there were 5 zeros and only 3 poles, so there was 2 leftover poles at 0 that had to be there, and those stayed with the minimum phase. And in the case of the all pass, everything's accounted for. There's a pole and a zero going together, so there's no poles or zeros in there, right? In the case of doing the minimum phase, though, or the linear phase, then we have a slightly different objective in mind. In the case of the linear phase, we still want to have the same minimum phase system, but we can have part of that minimum phase system now be in the linear phase system. So what we do here is we want to take any zeros that are outside the unit circle on the original system, and we're going to have those be part of a linear phase system. So we'll create a linear phase system that has a 0 inside and a 0 inside over here to be a quadruplet, and then we'll have a doublet. We'll have a 0 that's outside and a 0 on the inside. So that constitutes the linear phase system that we would create. And then, of course, we have 6 poles to match with that. And then the minimum phase system just has everything that's left over when we took on the job of we took these 3 zeros away from being reflected inside over here and have those in the linear phase portion, and then whatever left over is there. And, of course, when these 2 go together, it has to get back to the original.
Why are there 4 zeros on the minimum H-min of the...
Okay. Let's make sure I did that right. Okay, originally there were no zeros in there, but in this case, because we've rearranged things slightly, there are 6 poles in here, so there's 2 zeros and then 4 more zeros to balance it, right? Is that making sense?
You got to that minimum phase, like what's the difference between that minimum phase and the one directly above it?
Okay. Let me try to make this visible at the same time. Okay, on the original minimum phase system, I was going with an all pass. But now here, I'm going to take this 0 that I reflected from here into here, and it's now sitting over in here.
So you turn the all pass into like a linear phase and then create a minimum phase out of that?
There is no all pass left in this version. There's just linear phase and minimum phase. So what I have to do then is when I'm going to create this linear phase, I need to make sure that I put an extra pole in here that's going to cancel out that 0 when I go back to the original system. So I add some poles to the minimum phase and I do the same thing for here and for here, and then that pole was added in to get rid of that. Good. I want you to know this is how often you use this in your life. It's just like a lot of things in engineering. It's just things you can do. But I like the concept of this is that it's just your understanding, and you're being very fluid in how you can model systems with poles and zeros and just sort of keep things alive, basically. I mean, when you built your equalizer, what did you do in the equalizer problem? You went with an all-pass equalizer, but all you really did in that case was you just said, I cannot build the inverse of this system because these will be poles on the outside, so you just made it a minimum phase system at first, moved all the zeros inside, and then inverted this thing. So you created the inverse, which meant all of these poles become zeros, and all of those zeros become poles, and that was the system that you drove your signal through. Only one person did that totally correctly in this class, but at any rate, I'm not going to, I could ask an inverse question. I could certainly ask you, is there a stable inverse, and just be another picture, right? But it could be based on this idea, I guess, the minimum phase. I like the all-pass better myself because you can leave the all-pass filter out because it's just a constant magnitude filter with phase, whereas if you wanted to do that down here in this representation, you can't because part of the frequency response is in this linear phase system. So you cannot survive with the minimum phase all by itself in terms of getting the full frequency response magnitude. I didn't write this theory down, though. It's just a known theory idea in the community of DSP. So does that help with that question or that idea? I'm writing the final not to be long and tedious and burning your brain out. I'm wanting to you be able to just, if you can draw pictures to get the answer, and I'll give you a space to draw the pictures and everything, it's easier for you to do it, and it's definitely very easy for me to grade. It's almost like grading a fill in the blank or matching or something like that. I've never really specialized in that in my teaching, but I know when I was a student how many those types of exams have you taken in your life as an undergraduate? You take a lot of them, right? Match. I just can't even, I think back to my career. I took a whole year of music appreciation. I remember we had a lot of that in that class, this composer, this piece, and you had to just memorize stuff. And the library kept all the old exams, so you could study lots of old exams and just see what they came up with. So back over to here. My mouse is acting sensitive as usual. Turn that off, and then I can use my finger. So structures. We haven't had anything with the structures, direct form 1, 2, transpose, direct form 1, 2, so definitely a problem on that. It'll be a simple one. It could be, basically it comes in one of two variations. It comes in, I give you the h of z, and then I say draw a particular type of structure, direct form 1, direct form 2, etc. Or I give you a signal flow graph, and I say figure out what h of z is. Now, if I was to ask you which one of those would you prefer, your answer should be I'd rather just draw the flow graph from the h of z, because going from the flow graph back is the tedious problem, where you have to figure out all those equations from the flow graph and then go back. I'm not sure what I'm going to do. Does everybody agree? If I say, what would you rather have? You'd rather have h of z2 flow graph, right?
Both of them are very confusing.
They are confusing, so what don't you like about them, or what would you like to look at?
Well, block diagrams are just easier for me to understand when you do the flow graphs, and the arrows are pointing different ways. I don't really get it. Could you maybe go over one of those homework problems that we did to do on Friday?
Yeah, I can. Okay, let's trying to think where I can get access to one. I can go back to the notes, right?
Yeah.
Okay, I can do that. So I want to go to 6. This is a very simple one, but then the messier one that I went through is this one. So is this one that got you all riled up about confusion?
Yeah, all of them are just very confusing.
Okay. I look at it as easier than Ohm's law and mesh currents and node voltages, but so what you have to do if I give you a problem like this is you have to methodically go through, right? And here I just exhaustively did the whole thing. And I recommend if I give you a problem, I won't give you really, like an FFT signal flow graph is in one of the homework problems, where you're just following a branch through to show that that is part of the calculation for the DFT. That's one of the homework problems where you make a copy of an 8-point DFT and then you highlight a plot through it and then show that all the calculations along that path are correct for contributing to the DFT. More complicated than this, though, in the sense that it's got a lot more branches on it. So what I would do if it's a simple flow graph, and that's what I'm going to be giving you, you just write down the equations, be exhaustive, just like you were taking a networks problem from circuit theory and saying, okay, node 1, W1. I just look at it and I say branches coming into this node, there's 2 branches. They're entering that node, and that means they're summing together. So I have, what's that, W4 comes in there, and minus 1 times X of it. And I can do that in my head, right? I don't have to put a name on this node. I can just say it's X1 coming through here. And then I continue to go down. So which one, what other node do you want to pick just to see how it works out? It's confusing to you.
This one makes sense. Going from the signal flow graph to the equations is easier than going from the equations to the signal flow graph.
Really?
Yeah, like putting the weights on each node.
Okay. Well, I'll jump back to that then, because that occurred earlier. This was a block diagram form, but this could have been a signal flow graph. So.
No, I can't do that. Yeah, I can. This one's more straightforward.
Yeah.
Okay. Well, I'm glad we're having this discussion because I'm trying to remember I have that in here.
Like that.
Yeah, okay. Yeah, okay. So here's H of Z. And if you wanted to go with a direct form structure, this is the direct form structure signal flow graph. So let's back out here a little bit. So if it's a direct form structure, then this is all your feed forwards that are sitting over here. So that's this. It just follows out naturally. The direct path from that numerator is 1. It comes right straight across. And then 2z to the minus 1, it's coming out that path, and then z to the minus 2 times 1, and it comes out. And then the feedback paths are just from the denominator. But because of the way the notation works, and that was established in the class, the minus sign now, all the signs flip. So we have the direct path here, which is the 1, and then we have to flip the sign by convention. Actually, because when you write this around in a feedback path is where the minus sign were to come in, but you just automatically flip the sign. You see minus 0.75, you change it to 0.75, and then the next one is plus 0.125, so you change it to minus 0.125. one of the homework problems I know gives you a big, long structure, and there's no unique solution. Everyone's going to do it somewhat differently, so when I grade that problem, I will just look at it and see, are they all in there? Because everybody, you can mix and match in that one.
Of like the arrows and how they're pointing will always like remain the same between like the feed forward and the feedback.
Exactly.
Right, okay.
In the direct form too, and that's a good comment. So these are where the feedbacks occur on the direct form too. They're on the input side. Everything is cycling around, and then the feed forwards are on the input side. And this is how it started. I've always thought this was one of the easier things coming at the end of the semester. I mean, I never liked a semester where it got harder and harder right to the very end. I feel like in this class it kind of peaks at homework set number 6, and then we're slowly writing it down to the end with much easier things, much less writing, much less thinking, much less density on the page, and easier time for me to grade too. I mean,
Do you have a preference between like direct form 1 or direct form 2, or is it up to us to?
well, I will say in a problem, I might give you this, it might just be a variation on this problem. I'll say, give me a direct form 2, or I might say, give me a transposed direct form 2, which is just flipping this around. And then you reverse all the arrows, right? If I, you're talking to me now and you're letting me know that you're nervous about stuff, so maybe I just don't try to go too far with this. I try to keep it simpler. I'm for that. I mean, I've struggled. Grading the papers last night was not as easy as I was hoping for, and it's happened on both exams, so I'm fine. I will keep that in mind.
So if you were us, like, would you start first with the polls first and then go like 0 for
Well, the polls would be only if we factor. We don't know what, it's just the coefficients. It's
Right,
better
yeah,
to say,
cool.
not the roots of the polynomial,
Right.
but the
and then
coefficients.
the stuff on
Yeah, the coefficients.
Yeah.
Like direct form 1 is like a lot more intuitive immediately.
Yeah.
Oh, and no, it is, absolutely. It's the one that, I think it's called direct form 1 because it's like the one that just follows immediately. And then direct form 2, as the notes talk about it, was taking this and saying linearity, I can slide this over to here and then make these merge together, the common backbone. I visualize it as two people sitting with their backbones back to back. And then cascade, second order sections, and the other variations. I don't do a whole lot with this on the exam. I want it to be something simple. I want it to be memorable as, oh, I memorized how to do this and I'll do it, so.
The same thing would be great, Doctor.
This what?
The same thing.
Oh, well, I have to look in my catalog. Okay, so we are getting,
If you were asked to, let's say, put it in direct form 2, would it be like the most straightforward to put it in direct form 1 first and then convert that to direct?
possibly, if that's how you want to think, if you want to think step by step, I wrote my dummies book, and one of the things the editor said, in a dummies book, we emphasize steps. You want to lay out steps, and I think our life is like that. I mean, when we solve problems mentally, we think, okay, step 1 I can skip. For a particular type of problem, I'll just go right to step 2. But if you need to take it step by step, I can remember, not arguing, but I can remember my editor just over and over again, give us the steps. She would critique my writing and say, I want the steps, I want the steps. So, yeah, that's good. And I would expect if I see scribbling on your paper and then you rewrite it, redraw it, and then put a circle around it or whatever, I will understand that you were wanting to draw out direct form 1 and then direct form 2. Okay, so moving on, because we're going to run out of time here, I want to do some cool demos here with the time that remains. Not likely for FIR, finite precision effects, concepts at the most, but I would say I'm just gonna be bold here and say I'm not going to go here at all. Just take that out of this. But you had fun with the problem, right? With the noise analysis, everybody did that problem pretty much perfectly, and I think that was. And you're also doing speaking of noise, you're looking at quantizations or sensitivity to coefficients in the homework, right? You're just tweaking them slightly. That's our finite precision effect. So, okay. And I'm going to post this. I will try to remember to save this from the Edge browser here, and then I'll post this. The blank one will stay there, and then I'll add in the marked one. Okay, so now we're into spectral analysis. So something with the spectrum analysis like is shown on the bottom of the page, the basic spectrum analyzer design. What sampling rate would probably come first, but I might just give it to you. We're running at 10 megasamples per second. We want to have a resolution of so many hertz, fs over n, and so we want a delta f value is the typical way that I would do it. Then you have to come up with n, and then you have to make it the next higher power of 2, so you meet or exceed the requirement. And then I might say, what DFT point is going to correspond to 2.5 megahertz or something like that, which one it will be closest to, or something that it's going to involve the other equation here, where it will be K is in the frequency axis is K1 Fs over n, so something involving that. If I was doing this for the first time or pretty fresh, I would actually just have this sheet right with me, because it's right there. I'm just trying to simplify it down to what I call the back of the envelope calculation. And it also brings out another point, that if it's a real signal, this point will also show up over here, so that's the mirror image point, right? There's a symmetry, that just shows the symmetry property too, for real signals. If it's a complex signal, then it's unique. Software-defined radio project definitely lays heavily into that. So, are we good? I want to use some time for other stuff, multitasking, of course. Okay, just on this problem, on this project, the optional radio project, I wrote a reader example, and it's got some of the things in it, but the most important thing in this document, it has the problems you're going to do. Simple. Look at the spectrum. Use what you learned in project 1 to find the frequencies of interest. If you were an interrogator, you wanted to see where to find them. It's right here in this problem statement. That's a pretty easy one to do right from that notebook. And then next one is just simply looking at filters that I've already given you the designs for, and verifying its linear phase from symmetry, and verifying in part B over here that using the group delay function, it's constant group delay, and why is it constant group delay, or what is the group delay value. Remember, the group delay for an FIR linear phase filter is the mean delay the signal receives in going through the filter. So if a filter had 101 coefficients in it, the coefficient at 50 would be the mean delay. That's the average time it will take a signal to go through the filter. Then the next parts in here are where it gets to be more fun. You're going to complete a study, and that study is started over here. This is right out of the sample notebook, entered out to PDF. You're going to drop way down into here where you design channelizer, and the channelizer is composed of 5 bank 1, I call this bank 1. Bank 1 is what comes out of here in an array, to break it into 5 bands. And then you can have 5 bank 2s, but you're never going to implement that. I decided that was just too complex, so you're going to just do them one at a time. So I take, in this problem, you have to look at the block diagram for the system, and that's way up here. Well, it's not way up there, it's down here. Forgotten the order that I put stuff in. Here's the 5 bank 1s, though, and when I pass my SDR signal through that, the example I go through in the notebook is this bank 3. They start at, the indices in the output array are 0, 1, 2, 3, and 4. They're the matrix. And it comes out, and I'm getting myself all wrapped up because where did I put that picture? I've lost track of it. It's over here, though, for sure. Yeah. I spent hours drawing this thing out, but I wanted to explain how the function works, even though I've given you the code. So you put a signal in, and it goes through this transform domain filtering. The filter bank is set up in here either as odd or even. You can always use odd. I created this thinking I was going to need it, and then in the end, I messed up on it. It's not needed. But anyway, you come out with this array. So each row, k is equal to 0, 1 through k minus 1, is a different signal that's been filtered. And then you might have captured these two, and so on and so forth. But in this problem, then, I'm focusing on the red one is what I go through in here, and then I go ahead and just go through bank 2. This is the design of bank 2 in the notebook, and then when I change out the noise and set scale noise to false, these are the signals. And this is the cool thing that I thought some of you really got excited about last week when you saw all of a sudden now those 2 signals that were in the first bank, number 3, now I'm in, and I'm just working with that bank, and I've got all these channels that I've channelized into, and there's my one signal, and there's the other signal. We listened to this signal at 1300, remember? It was talk radio, talking about the Super Bowl or whatever. You can listen to that again if you do this project. And then you can just pull out the other bank, and the really cool thing about it is the way, and I wasn't going to do this, but I'm kind of got myself sucked into it here. The code that I take to do that then, to eventually demodulate it, once I figure out which bands I want, which is in this document, I figure out that the 5 band signals of interest were at index 1, 4, and 10. So, and that 1300 corresponds to 10. So then I go ahead and take the final step, and I work with the bank 2 output. I take row 10, take all of it, I decimate by 30, and then I envelope detect it with the absolute value, and then I DC block it with this low-pass filter that's in the block diagram, and then I use the audio function, and this should be a graphic control that disappeared when I rendered it out here, but then you can listen to it. Just click the button and listen to it like I did last week. Then you're going to do that for a different signal. You're going to change the 10 to a 4 and listen to what's there, and tell me what you hear. You maybe hear noise, you maybe hear more than one signal, you maybe hear one signal. And then the other part of the project, though, is to just go through and go to the other banks in the system. You're going to go back up to bank 1, and then you're going to recover a different bank from there. You're going to go through, here I went through 1, but then you're going to go through different bank 1. That's in in 4. And then in 5, I ask you to investigate the accuracy of the band centers. That comes out really nicely and obvious. And then the final one is to just pick 2 signals that you demodulated from all the banks that you liked the best and save those as a WAV file. So see, it doesn't show in this document because it's only over here. You might have an idea in mind of which ones you want. Like, I haven't listened to all these yet myself. I haven't listened to these. The orange one, I have listened to that strong orange one. That's definitely a very political thing. It's a left or right-wing political thing. I didn't want to show that in class last week, but listen to that one. That one's kind of cool. I asked you to set a threshold to only take the higher signals, but and then you'll send that to me as a WAV file.
So each of those 5 bands are separate radio stations?
No, it's breaking it down stage by stage. So what you're doing here is you are channelizing it first into 5 bands that are 240 kilohertz wide each, and then you decimate by 5, and you don't have to do any filtering or anything. You just simply take every 5th sample, feed it into this band, or feed this one into the channelizer, and then you do it a second time, channelizing with much narrower bandwidth, and then you decimate by 30. So you just take it step by step. I could not do it all at once because the filter orders were just too big to reach 300 tap plus filters. So I do it in 2 stages. But it achieves the intended goal, and when you channelize the first time, you get to see what's in those subbands, and then you channelize the second one to get the individual stations, and that's probably the coolest thing about the project is when you get to the individual signals. I'm getting my documents confused here. I'm going to try to work on this document and get everything into one document, but I haven't done it yet. This is at bank 1, so you can see clearly, but then when you finally go into bank 2, as I've already done in the notebook, you design the filter, do the noise modeling on it, but then here, this is the true idea of the channelizer. Each individual band now only contains nominally 1 signal. It's all isolated. I can just directly detect on it and not have to worry about another signal being in there. There is some leakage, like in here. This adjacent signal is showing up through the orange signal because I only have 50 dB of stop band attenuation, but still this is much less than the strong signal, and you just don't hear it. You won't hear it. You would design for all of that if you were building a channelizer for doing this idea of concurrent signal processing. That's the big thing with this concurrency. I don't have everything I need to know because I'm not cleared on it, but I know people are doing it, and I know they're doing it for intelligence gathering. But concurrency could be useful in another way. If you're a base station and you're operating with all the bands, you're doing concurrent processing there too. So it's pretty cool. Okay, now, if you do the adaptive filters project, and I've got just a very few minutes to go through it, we'll go over into here, and I have it running in here. I've got a lot of details on the algorithm. One thing I do want to point out, one other thing though, and that's here. I changed this yesterday, and I bumped into this last night when I was trying to get this notebook that I'm sitting in right now to work, and that is in my sample code. I've now got something in here and the hint section. See where these red bars on the side? Python has now changed in the way I import so you just can't use random. You have to put random dot in front of it. Most of you might know that already. And then this was yelping at me. I was directly going to take the output of this function, which sends out an array, and trying to push it into an array indexed at that k. Python now saying it's doing that is deprecated. It's eventually going to quit working. So I modified my code by writing to an array, a temp array, yfilt, and then I just take the 0th element of that and push it into the kth element of that, and then Python was happy. You can understand, right? Software keeps changing, and they deprecate, and they do things to make better quality code. So now I'll go back to the notebook, and so this is the type of thing that happens with the notebook. And I have a function here which is what you have to write, the algorithm you have to write up, and it shows that when I'm trying to adapt with, this first case is 10 dB, the minimum mean squared error in the filter eventually converges. It's coming down. It looks very noisy, but this is definitely better than at the beginning. It converges. So when that happens, what's happening in the output waveforms is the input waveform is pretty noisy, and then the orange is in steady state way out at 900 samples is where you look at it to see that it's converged. And if you look at the FFT or the DFT of the filter coefficients, it looks like a filter has formed a passband right around that signal and it eliminated the noise. At 0 dB, it's noisier, but you can see that it's still cleaning up, getting a pretty nice passband. For the square wave, it works similarly, but it's a lot harder to see because there's so many harmonics in it. And the square wave doesn't get particularly square looking, but you can see that it's working hard at trying to put passbands around all the harmonics of the square wave. So that's kind of cool. The optional problem, I'm not going to go into that. This is a hard optional problem to get to work right. So there's no optional problems in the other channelizer problem. But then turning around and doing interference cancellation.
Paint the sockets in the wall.
You've heard this before, right?
Yeah.
Paint
my
the
favorites.
sockets in the wall. Don't.
Sorry. So now you add noise into it, that speech, and when you add noise into it, it's a tone jammer. That's what it looks like. And if you go to listen to it, I'm just going to go for the 0 dB one. That's the better one. This is going, or minus 10 dB. So this is the dB level of the interference. And that's massive, right? It looks like really ugly. And here's what it sounds like.
Paint the sockets in the wall.
Now with the adaptive filter,
Paint the
listen
sockets
carefully.
in the wall. Paint the sockets in the wall.
Hear that little blip at the beginning? That's how fast it
Paint
adapts.
the sockets in
and
the
it just
wall.
tracks on it then. So it's pretty cool.
Really like newspapers back in the day would do that.
Oh. If you want to come talk to me, I'm going to go up to the lab for a little while and decompress. I didn't ride my bike, so I'm walking home today. I'm looking forward to a nice walk. It's been fun. We'll be talking more next week, and I'm sure I'll be talking to you. Remember, we can always do on Slack. We can do audio calls on Slack. Just keep partitioning your time, focusing on what is still happening. I've had fun teaching it. I don't know. I'm getting older though. I don't need to do this. I don't need to do this all the time anymore.
Are you teaching anything next semester?
No.
Yeah.
I will substitute though in Com 1 probably at least once.